Remember that from each point like x of the domain, a differentiable function like f increases most rapidly in the direction of the gradient, which is basically the rate of change at x being the magnitude or the norm of the gradient at that point. And the function decreases most rapidly in the opposite direction of the magnitude of the gradient. So basically, you find the gradient and then you take the magnitude or size or norm of it and multiply by negative sign. We have a lot of applications for gradient and directional derivative. For example, in machine learning, deep learning, the gradient descent algorithm uses directional derivative that tells us how the loss function changes as we move in a certain direction from a given point in the parameter space. In machine learning, we typically want to minimize the loss or error function. The gradient of the loss function provides the direction at the steepest increase in the function, so moving in the opposite direction of the gradient helps to reduce the loss. Now let us go back to our calculus. We're going to go over a few examples. Question says, find the direction of maximum, minimum, and zero change. Find the derivative of the function in three independent variables at the point 1, 1, and 0 in the direction of vector v, which component 2, -3, and 6. So let us find the partial derivatives of the function first and then evaluate that at 1, 1, and 0. The partial derivative of x cubed minus xy squared minus z with respect to x is 3x squared minus y squared. And remember that z acts like a constant, so it becomes 0. So when you plug in 1, 1, and 0, you get 3 times 1 minus 1, or basically 2. So this is the rate of change of function with respect to x-axis at the given point 1, 1, and 0. Now let us find the partial derivative of x cubed minus xy squared minus z with respect to y. So x and z both acts like a constant, so the derivative becomes 0 minus, here you have 2xy minus 0, you end up with -2xy. Let us plug in the point 1, 1, 0 into the partial derivative of f with respect to y. It becomes -2. It doesn't have any z, so you don't have to even plug in z anywhere. Let us take the partial derivative of function with respect to the third variable, z. Here, these two, they don't have any z in them, so it becomes 0. It's just a constant. And when you're taking the derivative of -z with respect to z, it becomes -1. Well, since it's constant, no matter what the point is, it always becomes the constant -1. So our gradient is 3x squared minus y squared, -2xy, and -1. Then at each value, at each point, we can easily find the gradient, for example, in this case 2, -2, and -1 as a vector. So the direction of v is obtained by dividing v by its length. Remember that the magnitude of v is equal to 2 squared plus -3 to the second power plus 6 to the power 2, which is square root of 49 or 7. Then we can find the unit vector by dividing v by its magnitude. So you end up with 2 over 7, -3 over 7, and 6 over 7. Remember that the gradient of f at the point, as we calculated, is 2, -2, and -1. Now, the derivative of f at p sub 0 in the direction of vector v is going to be the directional derivative of f in the direction of unit vector u at the point 1, 1, and 0, which is basically the dot product between the gradient and the unit vector. You just need to find the dot product between the gradient function and the unit vector, which becomes 4 over 7. We're just doing the multiplication component-wise, and you get 4/7. So as you can see, the directional derivative is a positive value. So going back to the same question, we are interested in finding the direction where f changes most rapidly at this point. Now, what are those directions? What are those vectors? Remember that for each point like x at the domain, a differentiable function f increases most rapidly in the direction of the gradient. So what you just need to do, you just need to find the magnitude of the gradient. We already calculated the gradient in the first part. It is 2, -2, and -1. And the function decreases most rapidly in the opposite direction. So basically, since you can find the magnitude of the gradient to be the square root of 2 squared plus -2 squared plus -1 squared, which is square root of 9 or 3. And the magnitude of the gradient is -3. It basically gives us the maximum rate of change and minimum rate of change. In what direction does f changes most rapidly? In the direction of the gradient. So as long as you have the gradient, which is 2, -2, and -1, you have the maximum rate of change, which is 3. In its opposite direction, you get the minimum rate of change, which is -3. Let's go over another example for you. Steepest ascent and descent. Consider the bowl-shaped paraboloid z equals to 4 plus x squared plus 3y squared. If you are located on the paraboloid at the point 2, -1/2 and 35/4, in which direction should you move in order to ascend on the surface at the maximum rate of change? What is the rate of change there? Well, at the point 2 and -1/2, the value of the gradient is, here you have 2x and 6y, which is giving you 4 and -3. Therefore, the direction of steepest ascent in the xy plane is in the direction of the gradient vector, which is 4 and -3. Or you can write it in basically the unit vector form by dividing the component by square root of 16 plus 9 or square root of 25 or 5. So this is give you the direction at which you have the steepest ascent. The rate of change is the magnitude of the gradient, which is basically 5. You can visualize this way as well. Here you have your paraboloid, z equals to 4 plus x squared plus 3y squared, and at the point 2, -1/2 and 35/4, if you plug in 2 and -1/2 for x and y, z becomes 35/4. And here you have the steepest ascent, and in the opposite direction, you have the steepest descent. Next part of the question. So we are going back to our paraboloid. Now, if you are located at the point 2, -1/2 and 35/4, in which direction should you move in order to descend on the surface at the maximum rate? What is the rate of change? So as you saw, the direction of steepest descent is the direction of opposite of the gradient function. So you basically multiply 4 and -3 by negative sign, and you get -4 and 3. Or if you think about it in the unit vector form, you divide -4 and 3 by the magnitude of this vector, which is 5. The rate of change is minus the magnitude of the gradient, or -5. As easy as that. And finally, let's go back to our bowl-shaped paraboloid. we are interested in knowing that at the point 3, 1, and 16, in what direction is there no change in the function value at all? So at the point 3 and 1, the value of the gradient is 6 and 6. So this is your vector. The function has 0 change if we move in either of the two directions that are orthogonal or perpendicular to this vector. These two directions are parallel to 6 and -6. In terms of unit vector direction, where we have no change, the unit vector is -1 and 1 divided by the magnitude of the vector, which is square root of 2. And also, if you multiply by negative sign, you get 1 and -1 divided by square root of 2. So remember that when we are talking about orthogonal vectors, two vectors are orthogonal or perpendicular if the dot product between them is equal to 0. So if you find a dot product between these two vectors, it always is 0. 6 times 6 is 36, minus 6 times 6 becomes 0. So that's how you can easily find the orthogonal vectors.